Hi, we're going to take a detailed look through the means of reading a section, and today's section we're going to talk about is 11.1. And this is an introductory section for a new chapter, so understandably it contains a lot of material. Remember, if you have not yet done your perusal, make sure you spend about a minute per page, which in this case is 5 minutes, just familiarizing yourself with the concepts, the ideas, the things that are going to be in this section that you're going to want to dig through. So if you have not yet done that, go ahead, pause the video, and then come back. Welcome back. What we're going to do is take a look at this section. This is not a replacement for reading the section. I just want to highlight some of the approach and methodology of how you would do that. So starting on page 630, there's a description here for autonomous systems along with an example of what an autonomous system is, which is the set of equations labeled 1. And this is, again, as it is in almost all textbooks, it's just a general representation. And they note for us, very importantly, that the independent variable, in this case t, does not show up in any of the equations, and that's what makes it autonomous. And then, of course, example 1, they give us an example of something that's non-autonomous. What I want to point out, though, here is in the middle of the page is the sentence, compare 1, equation 1, with the general system given in equation 2 of section 10.1. This is the kind of thing where you want to actually do that. Go back to section 10.1, look at what the author's talking about, and understand the connection that he's trying to build so that you can better understand the material. So I leave that to you, and what we're going to do is just continue moving forward here. This is an example of a non-autonomous system. And while this section is not titled nonlinearity, a lot of what we're talking about is nonlinearity, because if it was linear, then we could use the techniques and ideas that we discussed in chapter 10. So down at the bottom of page 630 is another thing that is familiar from differential equations, which is how to convert a second order or any higher order ordinary differential equation into a system of first order differential equations. And I just want to take a brief moment to look at example number 2, where they talk about the pendulum. This is all familiar to you. I just want to point out that the author's selection of using x and y here, I disagree with. I think that it's much easier, particularly when you have an application, to use descriptive variables. So there's absolutely no reason to relabel theta as x. It doesn't add any value to the problem or to our understanding or communication of the problem. So I would just leave the theta as theta. And then the question is, what is theta prime? Theta is an angle, and the rate of change of angle is most generally referred to using the Greek letter omega. So this is how I would set this up. And then the system of differential equations becomes theta prime equals omega, and the second equation is omega prime equals, and now we have to solve the equation for omega prime, which is minus a g over L sine theta. And it's worth noting here, so we have a system of first order ordinary differential equations. It is autonomous because we do not see the explicit representation of a t anywhere, which is the independent variable. It's also nonlinear, and it's nonlinear because of this term here, right? So, and it's worth noting we cannot represent, so remember back to the linear algebra portion of the course. We might want to represent this so that we can use all of our powerful linear algebra tools. We might want to represent this as some kind of a linear system with a matrix. And so we have our vector of unknowns, which are theta and omega. And now the question is, all right, how do we fill out the elements of this matrix? And the answer is, we can't do it. There is no way to represent this. So remember back to linear algebra, if we can represent the function using a matrix, then it's linear. And if we can't, then it's not. So it's nice that those two things go hand in hand with one another. Moving on then, they talk about some representations here. It's very important that you understand the difference between x vector prime equals ax in the case where we have something that's linear, and the much more general notation that they're using here, which is x vector prime is equal to some function g, and of course we apologize for the confusion because we're using a g here and a g here. This, of course, g up here is the gravitational constant. G down here is the function of the right-hand side, and this is a function of the vector x. In this notation, we're in a situation where as long as it's first order and as long as it's autonomous, we can represent it this way. So we can include all linear and nonlinear systems in this representation. Following then, you want to read through and make sure you understand the definitions about dynamic system and the state of the system. And the big point that's coming through this paragraph here is the fact that if we have an autonomous system, then the evolution of that system, the x prime, the rate of change, what we call the evolution of that system is based only upon where we are right now, what the values of the x vector are. And it doesn't matter about what time it is. It doesn't matter what the value of the independent variable is because it's autonomous. At the bottom of page 631 is the vector fields in interpretation. And let me just highlight here a little bit. What I want to do is point you back to chapter 9. So all the things that we covered in chapter 9 that relate to vector fields, and what they've done is they have a vector representation, and they've set it up to be the first component is P and the second component is Q when we're adopting the form that they have where x prime is equal to P and y prime is equal to Q. And then the plot of this for each value xy, so if we go in and look at each value xy, what we're going to have, we plop down in some position and we're going to have an x direction component based upon P and a y direction component based upon Q, and we're going to end up with some arrow. So you're familiar with this from the phase plane plots. You just have to understand that as long as it's autonomous, we can use the phase plane to come up with this picture. Moreover, what I want to do is just show you how this concept expands in the situation where we have, oh, it's not a vector, x is equal to P, which is a function of x, y, and z, and then y is a function of x, y, and z. Notice I am specifically making them non-autonomous. There are no t's here. And r is a function of x, y, and z. So this exact concept holds just the same. We have a vector valued function, but in this case 3 dependent functions. And that's going to give us a P, which is a function of x, y, and z, and then a Q and an R. And so again, all of the material that you've learned in chapter 9 applies when it comes to vector fields. Concepts like divergence and curl and those types of things. So you want to read through, make sure you understand in detail what they're pointing out when they're making these analogies and having these conversations and talking about the rate of change. So example number 3, they're just giving you an example of the material that they've discussed. Highly recommend in these types of situations that you use the appropriate tool. Go find some phase plane plotting device and actually plot out these equations and regenerate figure 11.1.1 so that you understand how that figure was developed. Following on, the types of solutions. So in this case, we have to read the hypotheses. We have to read the conditions under which the following statements are valid. So we have to read carefully. If P, Q, and the first order partial derivatives, partial of P with respect to X, partial of P with respect to Y, partial of Q with respect to X, and partial of Q with respect to Y, are continuous in a region of the plane, that's the XY plane, then a solution to the plane autonomous system given by x prime equals p, y prime equals q, that satisfies an initial condition, x at 0 is equal to x naught, is unique. Moreover, we have one of the three basic types for the solution. So there's a lot that's contained, and this is typical in technical work. There's a lot that's contained in those couple of sentences. If you refer back to your ordinary differential equations, you realize that this condition is similar to the conditions for ordinary differential equations, individual equations. We're looking for continuity of the right-hand side. So we want the functions to be continuous and their first derivatives, in this case their partial derivatives, to be continuous. And then we go through and it outlines the types of solutions we can have. We can have an equilibrium solution, and we can have an arc or a trajectory, which is just a function, or we can have a periodic solution, which is still a function representation, right? Solutions for differential equations are always functions. Even in the case of the constant solution, it's a constant function solution. And what they're pointing out here is the notion that in number 2, the solutions are not going to cross. So the uniqueness of the solution means that they can't cross each other. And then down here in example 4, they want you to find some critical points. Following on the next page, 633, they do a really nice job, particularly in part B here, of explaining how there's no canned method for doing this. You simply have some equations and you're trying to find values of the dependent functions that will make it equal to 0. Because when the rates of change are all 0 simultaneously, that's when we have a critical point or an equilibrium solution. So I would look through that example in detail. Similarly with example number 5. Now example number 5, it's worth noting, and this is the value of reading and understanding and being able to bring the pieces of the puzzle together as you move forward through a course. But let me just highlight for you, in case it's something that you're not seeing when you first look at it. Both x prime equals 2x plus 8y and y prime is equal to, whoop, these are not vectors, sorry. These are just the variables x and y. This is equal to minus x minus 2y. This can be written in matrix form as xy prime is equal to some set of coefficients multiplied times the vector of unknowns, which is the vector xy. And of course those coefficients are 2, 8, negative 1, negative 2. So by virtue of the fact that we can re-represent the system using matrices and vectors, what does that mean? It means from linear algebra, we know that it is a linear system. And so both examples A and B here are linear systems. And you already understand periodic solutions for linear systems. They occur when we have a center, when we have purely imaginary eigenvalues. And that's all that this is highlighting. Following is a concept that is near and dear to us, which is the idea of changing or transforming the problem into a coordinate system that makes the problem easier to understand, easier to analyze. So in this case, they are changing to polar coordinates. And what I wanted to do is just show you briefly how we end up in this situation. So they start with two equations. We have an r squared is equal to x squared plus y squared. And then we have theta, which is equal to the arctangent. So unfortunate use of the notation that's been adopted for decades is using the -1 as an indication of an inverse for a trig function. I highly recommend that you adopt the arc notation so that you don't get confused about when you're talking about an exponent versus an inverse function. So the arctangent of y over x. So what we're going to do here is we're trying to come up with equation number 2 that they have represented. So again, this is always worth your time. Understand where things come from. This again is how you build up your knowledge and build your intuition and build a deeper understanding of what's going on. So take just a minute and think about how. Now, note one more thing, right? We know that r is a function of t and theta is a function of t and x is a function of t and y is a function of t. And the question is, how did the author come up with the representation of equation 2? So take just a quick second. I'm going to put this on pause and think about how that would be done. All right, hopefully you've had just a little bit of time to think about this. So what we're looking to do is take the derivative of this set of equations, because we're moving to polar coordinates and we want to know what the rates of change in polar coordinates are, so we're trying to match up with what's in equation 2 in the text. So let me push this to the top, and the key idea here that we're going to be interacting with is implicit differentiation and, more importantly, with the chain rule. So what we have is we're going to apply the derivative with respect to t to both sides of this first equation. And of course we can do that because we can do anything to an equation as long as we do the same thing on both sides. And so we take the derivative of 2r, or of r squared, and we get 2r times dr dt from the chain rule, because r is a function of t. Similarly, when we take the derivative of x squared, we end up with 2x times dx dt. And we end up with 2y times dy dt. We can factor out the 2's, and we can divide both sides by r, and that's going to leave us with r prime is equal to 1 over r x times x prime plus y times y prime. And this matches exactly with what we have in equation number 2. For the next equation, we take the derivative with respect to t on both sides, take the derivative of the arctan, and I'm going to rewrite this quotient as a product. I don't use the quotient rule, I just use the product rule. And we're going to take this derivative with respect to t. So this is straightforward. This is theta prime is equal to, and now the derivative of arctan, if you don't remember, that's going to be 1 over 1 plus y times x, whatever the argument is, which in that case is this thing here, squared. So this is derivative of the arctangent. You can look that up on Google if you don't remember. And then, of course, chain rule, we're left with the derivative of y x to the negative 1 with respect to t. And now we're going to have a series of chain rules. Let me provide a little bit more space here. So continuing on, we have theta prime is equal to 1 over 1 plus expanding. This is y squared x to the negative 2. And then the derivative, this is going to be product rule. So it's going to be first times derivative of the second, which is minus x to the negative 2 power, and then its chain rule, this has a dx dt in it, and then plus the second, which is x inverse times the derivative of the first, which is dy dt. And so using the chain rule appropriately, we come up with this situation here. Now what we're going to do to simplify and match what's in the text, we're going to recognize that what they do is multiply by x squared divided by x squared. So they're going to multiply this through in order to come up with the formulation they have in equation 2. I'm going to erase this off. I just wanted to show you that is what we're going to do. So we multiply by x squared over x squared, and we have, of course, an x squared in the numerator, and then down here in the denominator we have an x squared plus y squared, because x squared times x to the negative 2 is just 1. And then rewriting up here, we have a negative y over x squared times x prime plus a 1 over x times y prime. finally, we're going to distribute the x squared into this sum. And when we do that, we have theta prime is equal to 1 over x squared plus y squared. And then distributing this in, we're going to have a minus y times x prime. X squared divided by x squared gives us 1. Plus, and then we have x squared divided by x is going to give us an x, and then we'll have times y prime. And this is what we see in the book, except they make the substitution. Of course, x squared plus y squared is r squared. So we end up with a 1 over r squared minus y times x prime plus x times y prime. Listen, this happens frequently in a textbook, and I know for many of you this is kind of your internal excuse to yourself as to why you don't read textbooks, is because equation number 2 here on page 633 appears to come from nowhere. So what's incumbent upon you is to understand, is to ask questions about, hey, you know, this thing is in here and I don't really understand where it comes from, and so I need to go do some work to figure that out. And by doing this work that we've done here, and it takes some time. Again, this, you know, reading technical work takes time, takes effort. But when you do that, now you've not only solidified your understanding of chain rule, but you also understand where equation 2 comes from. Moving on to the next page, we just have an example where what the text does is simply take those equations, equation number 2, and substitute in the information that we have here for a specific problem. And sometimes this works and sometimes it doesn't. Of course, in the example, it works very nicely. We end up with r prime equals negative r squared and theta prime equals 1. And so this is good information, and it's a very easy transformation. So the transformation of polar coordinates works sometimes. Sometimes it doesn't, but this is the reality of solving problems. We just have to try things. There aren't necessarily canned approaches and methods that we use to solve things. So that's the problem number, or example number 6, where they show us that information. And then similarly here on example number 7, they give us information that is already in polar coordinates, so we don't do the transformation. But then there's a nice discussion down here about what does it mean to interpret and understand what those differential equations are saying. And the result is we have a periodic orbit that shows up that looks completely different than what we see with purely imaginary roots. This is a different type of periodic orbit, and it's the reason that they emphasize periodic orbit over here on page 632, where they talked about the different types of solutions, and one of them that they pulled out, even though it's a function, they called it out as a special item, which is this periodic solution. So back to page 634, we move on and we're into the homework problems. So this is the approach that you want to take. You want to really dig in, really understand the items that are part of the lesson. Thank you for your time.